Okay, I believe you can see my screen and hear me well.
Yes.
Perfect. Okay. So, as it was introduced by Professor Odo, I'm Chandrasekhar Saraf. I'm a postdoc at the Korea Astronomy and Space Science Institute in South Korea, and my primary research field is cosmology, different aspects of cosmology. And I'm very happy to be speaking to the African community in general about my research and about cosmology in general. So, I believe I'll let's have a look at. So, this is a mandatory advertisement of my institute so I've joined the Korea Astronomy and Space Science Institute in December 2023 and been here for like 1.5 years as a postdoctoral researcher, and this is the main campus in South Korea. So if you are interested to know about the institute in general, you can look up at it at the official website. And my research motivations are slightly varied, but most of it is revolved around cosmology in general, specifically about combining different types of data, which we will learn about in this seminar, like the cosmic microwave background and galaxy surveys, and combining them together to understand our universe. So I employ a different set of methods. I also perform some numerical simulations to understand uh, how well we can measure the cosmological parameters. And then I also look for new techniques, new strategies which can be used on the data to understand the background truth or the physics of our universe. In addition, I also work in the perturbation theory from the mathematical approach. I'm very much interested in discovering new phenomena, new observables, and recently have also started working in the radio sources of on which Africa plays a very major role. We will look at it. So just to give a brief outline of what I'm going to talk about today is, so I'm going to introduce you to the standard model of cosmology called the lambda CDM model. We will look why this model of cosmology is uh, so popular. We will look for evidences for support of this model of cosmology. And then we will go further and look at what are the problems of this model of cosmology. And we will then look at some of the recent results and in between some my contribution to some of the cosmological research. And we will see what future gives us. So I suggest that if someone has a question in between, they can stop me, or if they need answer urgently to better understand what we are going to learn. And unless we will have more questions at the end of the talk. Okay, so first, let's introduce the standard model. So it is now completely accepted, widely accepted, that our universe began roughly 13.8 billion years ago in an event called the Big Bang. And I believe most of you must be familiar with this concept of Big Bang. And the entire evolution of the universe is kind of like a study area which comes into the domain of cosmology. That from the point of the Big Bang to the formation of the galaxies till now is what is all covered in the study in cosmology. So explaining all the bits and details into of all this 13.8 billion years will be a very difficult task, but we can summarize the understanding of our universe in five or six different stages, right? So after Big Bang, the first stage that happened was inflation. It's called inflation, quoted by here as number one. So when the universe was very, very small, very young, it was very hot. It underwent a very rapid expansion, very, very fast expansion. And this period is this expansion period itself is called the inflationary period, as the name suggests, inflation, which means uh, uh, getting bigger in size very quickly. So that's exactly what happens. So just after Big Bang, universe underwent a very rapid expansion, and we call this period inflation. Now, as the universe expanded, it slightly started to cool down. the energy in the universe, the energy density became lower, and the mean temperature of the universe started to cool down. And as this with this expansion and cooling down of the universe, small particles started to form, and with these particles were the first that were going around each other, uh, and very fundamental particles like quarks and leptons and photons and all the gluons and the other fundamental particles were the first one to be created. And as the temperature expanded slowly, as the universe expanded slowly, the temperature went smaller and smaller. And roughly about 380,000 years after the Big Bang comes a very important period in the evolution of the universe. This is the point where the first atoms started to form. The first hydrogen atoms from these fundamental particles began to form. The temperature of the universe was roughly at about 3000 Kelvin at that point of time. And with this formation of the first uh, hydrogen atoms, the photons became free to move around. Before that, the photons were continuously interacting with the particles. But now, once you have atoms, only certain photons can interact with the particles, as we know from modern physics, that once you have hydrogen atoms, only 13.6 electron volt of energy can be supplied to the photon, to the proton, the single proton in the hydrogen atom. And that's exactly what happened. Rest of the photons became completely free, and they were free to roam around in the universe. And this light, this was the first light in the universe, which we now, after 13.8 billion years, observe in the microwave band. You know, and that is why we call this the cosmic microwave background, because no matter where you look in the sky, this background exists. If you have a good enough microwave detector, you can measure this first light, and this has helped us a lot in understanding our universe, which we will see a little later. Now, soon after the formation of these hydrogen atoms, there was a period which is called the Dark Ages. Why is it called Dark Ages? Because it took some time to go from atoms to stars. And this is the period where there were atoms but no stars. And since there were no stars, that means there was no light. And in absence of any light, you cannot see anything in the universe. So just after this first light, the CMB uh, photons became free. There was a period when there was no light, and it was called Dark Ages. And soon after that, the first stars were formed. Then the first galaxies were formed, and then the universe keep undergoing into the expansion and forms all the large scale structure that we have in the universe. So if you have looked at any galaxy survey, all the structure that we see around us was formed much later than the universe after the universe was born. And right now we are in the fifth section, where the universe is undergoing an accelerated expansion. It's not just that the universe is expanding, but the rate of expansion, the rate at which the universe is expanding, is also increasing. And we believe this is because of something which we call dark energy. So, from 13.8 billion years ago, the universe started with a bang, which we call the Big Bang. And right now, after 13.8 billion years, we see all the beautiful cosmic structure that we can see in the different galaxy surveys. So, this is a brief history of how the universe came into existence and how the formation of structures actually took place. Now, the lambda CDM, which is the core uh, idea of this talk, is called the standard model of cosmology. And it is a model that helps us understand how the different phases of the universe actually happened, what is the physics that controls the different phases of actions, and what can we learn about the universe based on this underlying model. So the lambda CDM, or the lambda cold dark matter, that's what its full form is, lambda cold dark matter model, is based on certain assumptions. The fundamental assumption of those being that the universe is homogeneous and isotropic. which means no matter in which direction you look and no matter where you are in the universe, the properties of the universe will be same. That is what the homogeneity and isotropy principle in the universe tells us. Other than that, there are few key ingredients in the lambda CDM model. First, the lambda itself, dark energy. So, dark energy is believed to be the key reason why we are undergoing an accelerated expansion at present. So, that's one of the key ingredients which we don't understand well. The second ingredient is the cold dark matter, the CDM part. Now, these two things, dark energy and dark matter, are two of the most unknown uh, facts in our universe. We measure them, we indirectly see their effect, but we don't know what they are. So if you look at this pie chart in the right hand side, there is one for today, and there is another one when the universe was about 380,000 years old. So just at the time when the CMB light was free to move around the universe. So if you look, when the universe was young, it was dominated by dark matter. 63% of the universe was dark matter. 50% of the universe was composed of photons, and 12% of the universe was composed of atoms. And by atoms, we mean here all the atoms, all the baryonic matter that we can see in the universe in different wavelength bands, starting from all the way to gamma to X-ray and going all the way into radio. The entire electromagnetic spectrum is composed in this 12% and this 15% of photons. This is all that we see. And there was 10% of neutrinos. But today, we can see the drastic difference. The atoms are roughly 4.5% only, right? And you see that it has gone from 12% to 4.5%. Photons, which were 15% before, are nowhere to be seen. They are so when we compare this chart, we have to understand that this is not comparing the number of photons. This is comparing the energy in the universe coming from these different components. So right now, at present, photons do not contribute any energy to the total energy content of the universe. And we see that dark matter has also reduced from 63% to 26.1%. And what has taken over? Dark energy. Roughly 70% of the energy in the universe is coming from dark energy. And this is in two charts. You can compare the evolution of the universe going from a matter dominated, where the dark matter and atoms were dominating the physics of the universe, to at present, where the universe is dark energy dominated. Roughly 70% of the matter energy content in the universe is dark energy. Other than that, the fundamental assumptions of the lambda CDM model is inflation. Rather, how inflation happened is one of the questions, and we have to assume something about it. And second is that the universe is flat. When I say that the universe is flat, it means its geometry is flat. And when the geometry is flat versus curved, so a curve, for example, a curved geometry is that of a ball, a sphere like our Earth. It's called a positively curved geometry. But a piece of paper is flat. So the geometry of the universe is flat. So these are the key ingredients of the lambda CDM model. So we'll try to understand about some of them, specifically first dark energy and dark matter. So dark matter is something that we have observed indirectly in our universe. We don't know what it is, if it is a new type of particle that we don't know about. So, is it kind of like, is our understanding of the universe, specifically our understanding of the theory of gravity, is incomplete? And that is why we see this effect. So basically what happens is this, a very famous example to understand dark matter is the bullet cluster. So this is a group of galaxies not very far from us. And you can measure the mass distribution of this cluster in two different ways. You can look at the emission in X-rays. So if you have an X-ray telescope, you can point at this bullet cluster and you will see where the emission is coming from. And that X-ray emission is shown here in pink. And if you try to understand, and the other way is basically trying to understand the light from the galaxies which are behind this cluster. So just like in optics, we have optical lensing. In cosmology, we also have gravitational lensing. The light of the galaxies behind this bullet cluster get lensed, and if you measure the lensed light, you can understand something about this bullet cluster. So if you use this lensing measurements for this bullet cluster and try to understand the mass distribution, it will turn out to be in this blue region. So you can clearly see that there is that there is a mismatch between the uh, blue regions inferred from the weak lensing and the red regions inferred from X-ray. Now the key point here is X-ray measurements, the pink ones, only look at the atoms, the baryonic matter, but the blue ones look at the total matter, which is baryonic matter plus dark matter. So that is why we see the effects of these dark matter, but we cannot measure it directly. We cannot see it directly. And that's why it's still a mystery to us. And second most important is dark energy. What is dark energy? We have no clue at the moment. But what we see that it causes rapid expansion of the universe. It causes the universe to expand, and it's also making the universe expand faster with time. But we don't know what it is true nature. If it is some kind of new force, we don't know, because we know that there are four fundamental forces in the nature. If it's kind of like a new type of force we don't know about, or is one of our assumptions in the cosmological model, for example, homogeneity or isotropy, that's kind of like flawed. That's a wrong assumption. And because of that, we are seeing this effect of dark energy. We don't know at the moment. So I hope we are all set to look into more into look more into the lambda CDM model. So let's see, why do we believe that the lambda CDM model is a good description of our universe? We have to have some evidence, and we are trying to look at this evidence right now. First is the cosmic microwave background. So this is the first light that was generated in the universe when the universe was only 380,000 years old. And in that sense, it is the oldest electromagnetic radiation that you can see in the universe. It was first detected in 1965 by by mistake uh, by Arno Penzias and Robert Wilson. They were trying to study something else with their radio antenna, and by mistake, they detected this full background of the cosmic microwave radiation. Right now, uh, the temperature of this radiation is 2.73 Kelvin. So this cosmic microwave background radiation very well follows a Boltzmann distribution, and this is with the peak temperature at 2.7, sorry, follows a black body distribution, not Boltzmann, follows a black body distribution with the peak at 2.73 Kelvin. And there are some fluctuations in this temperature of the order of tens of microkelvins. And these fluctuations have informed a lot about the universe when it was 380,000 years old. So basically what you do is you measure the distribution of these anisotropies, these fluctuations in the temperature, and then you try to infer something about the background cosmology. So for example, figure on the right, there was an experiment to measure the CMB in 1992 called the Kobe Cosmic Background Explorer. And then in 2003, we upgraded to Wilkinson Microwave Anisotropy Pro, the WMAP. And in 2013 was launched Planck measurement from the Planck satellite from the European Space Agency. And you can see over 20 years how our understanding of these small fluctuations have improved. We are able to measure such tiny fluctuations that we can constrain our cosmology so well. So this cosmic microwave background measurements is one of the most important uh, discovery for modern cosmology, which helps us to understand our cosmological model so well. Next is something called the BAO, or the baryon acoustic oscillations. So what is this? This is basically when the universe was very young and all the particles and photons were, just going around each other in kind of like a dancing around each other in a in this very young universe. Due to interaction of these, there were sound waves that were generated. And once the photons became free to propagate, when the first hydrogen atoms were formed, these sound waves could not propagate anymore, and these baryon acoustic oscillations are basically the imprints of those sound waves which were there in the early universe. And most interesting thing about this is baryon acoustic oscillations act as standard ruler. That means if there is a baryon acoustic oscillation ring like this closer to us and another one that is far to us, their size will remain same. That is what exactly is shown in this first image. It doesn't matter where the BAO is. You see, their size is very well understood and we know its size beforehand. So, other way around, if we measure the size of BAO, we know how far it is. And that's exactly what is used by galaxy surveys like Sloan Digital Sky Survey or the ongoing one, Dark Energy Spectroscopic Instrument, to measure uh, the properties of our universe. And these baryon acoustic oscillations are very important to measure the expansion history, how the universe has expanded over last 13.8 billion years. So this has also helped to establish the lambda CDM model. And the third very important probe is the type 1a supernova. Now, type 1a supernova are also kind of like BAO in the sense that we know what is the maximum luminosity, maximum magnitude or brightness of a type 1a supernova will be. So if we measure the brightness of supernova, we measure some quantity, then we can figure out how far that supernova happened. And this helps us to again measure the expansion of the universe. And indeed, type 1a supernova were the first evidence that the universe is not just expanding, but it's expanding faster with time. And this was discovered by Edwin Hubble in 1992. And this accelerated expansion of the universe led to the discovery of something which we call dark energy right now. So we have looked at cosmic microwave background, we have looked at baryon acoustic oscillations, type 1a supernova, and now the fourth important key in constraining our cosmological model is the large scale structure, the entire large scale structure. What do you mean by large scale structure? Is basically how galaxies are distributed in the universe. So, for example, here I show some results from the Millennium simulation. It was a suite of simulations uh, prepared a couple of years ago. And this shows different sizes, different scales of our universe from simulations. So we see that in the bigger one, we see this structure like a web. And this is exactly what we call it, the cosmic web. And all of these points are basically galaxies. If you zoom in a little bit, you will be able to see this big cluster here with lots of, you know, fiber-like structures going on, which we call filaments. And they are very well connected to each other. And if we zoom even further, we can see this entire galaxy cluster here. And each dot in here, these big dots are basically galaxies. So how these galaxies are distributed in the universe basically tells us a lot about the cosmological model, about the physics that governs our universe. So these four important quantities are the pillars through which we understand our universe and which support till now our standard cosmological model, the lambda CDM. So now let's have a look that if all of these models support lambda CDM, what are the troubles in the lambda CDM model? Why are we still studying and doing all these experiments and doing all this analysis? It's because there are still, it's not that lambda CDM can answer all the questions. There are some challenges, there are some tensions, which are very important questions in cosmology at present. First, the very famous one, you must have heard its name, it's called the H naught tension or the Hubble tension. So we just learned that the universe is undergoing expansion, and the expansion is, the rate of expansion is increasing with time. And this rate of expansion is basically what is represented by this Hubble parameter. Now, you can measure this Hubble parameter using different tracers. First is the CMB, the cosmic microwave background. It gives you some information on what the Hubble parameter should be. And then you can use galaxies and supernova to measure Hubble parameter. If you do that, there is a difference in the value of Hubble parameter inferred from CMB. For example, here I have quoted value from Planck, the Planck satellite, which uses CMB measurements, and it gives us a value of 67.27 kilometer per second per megaparsec. So let's first understand what this value mean. This means that if two galaxies are separated by a distance of 1 megaparsec, they will be moving away from each other at a speed of 67.27 kilometers per second. So if they are separated at 10 megaparsecs, they will be moving away from each other at the speed of 670.27, 672.7 kilometer per second. So the farther the two galaxies are, the faster they are moving from each other. This is exactly what the accelerated expansion of the universe is doing. So if you use CMB measurements from Planck and try to measure this rate of expansion, you will find the 67, a value of 67. But if you use supernovas, which is very close to us, you will measure a value of 73. And this difference between the two values are very prominent. It's at a significance of 4.2 sigmas, which is a very high significance disagreement. So this remains still an open problem in cosmology as why this is happening. Why is this problem happening of H naught tension? Second, another important tension or challenge of the lambda CDM model is the S8 tension. Now, what is this S8 tension? So we saw that the galaxies are distributed in the universe, but their distribution is not random. It's not a random distribution. Rather, galaxies tend to come closer to each other. So if there is a galaxy, there is a higher probability of finding a galaxy nearby. So they tend to cluster together. And this S8 parameter basically tells us how strong this clustering will be. So if I have a very high value of S8, a lot of galaxies will be grouped together. If I have a very small value of S8, only few galaxies will be grouped together. So that is why it tells us how strong the clustering of matter in the universe is. Now, again, if we use CMB based measurements from Planck, and if we use the large scale structure of the universe at lower redshifts, we find a discrepancy in the S8 parameter, not as strong as the H naught tension, which was at 4.2 sigma. Here, the discrepancy, the difference varies between 1 to 3 sigma, but nevertheless, it's there. And we still haven't figured out a way to solve this. But these two, the H naught and the S8 tension, were the two most prominent problems in cosmology, but these are not just the two problems, there are other ones. For example, cosmic dipole anomaly, which is there is a dipole in the universe. And if you measure this dipole from the CMB or from redshift surveys, there is a difference between the value and the direction of dipole, and that's what cosmic dipole anomaly is. Another more philosophical ones are, for example, what is the nature of dark energy and dark matter? We don't know. We just need them to explain our universe, but we don't know what dark energy and dark matter are. Then there are some problems with the inflation that we have to tune the parameters of inflation in a particular way to reproduce our cosmology, our observational universe. Otherwise, everything breaks down. Then there is some trouble with the Big Bang nucleosynthesis model, that when the atoms were created, there is some missing information there which we don't know. And recently, James Webb Space Telescope, the JWST, gave us very high redshift galaxies, which directly challenges the lambda CDM model in terms of how galaxies formed in the universe in the first place. And there are some more, but this is basically the overall area where we look at open problems in cosmology. Now, let's have a look at some of the recent results in cosmology and try to see what they are telling us. Interestingly, in this year itself, there were two very rather contradictory results came out. One from the Atacama Cosmology Telescope, which is basically a CMB measurement in the Atacama Desert in Chile, and it's measuring the CMB sky at very precise resolution, at arc minutes resolution, and it's making very precise CMB polarization measurement. So CMB has a temperature measurement, and it also has a polarization measurement. So this Atacama Cosmology Telescope is focused on measuring CMB polarization because then we can learn something more about our universe. And the recent results from the Atacama Cosmology Telescope are very consistent with the lambda CDM model. So this suggests that our understanding of the universe within the lambda CDM model is correct. But however, there is a galaxy survey going on called the Dark Energy Spectroscopic Instrument. It is a spectroscopic galaxy survey which covers the northern sky, and it's mapping roughly 30 million galaxies, and it's an ongoing survey. Now, the DESI, or Dark Energy Spectroscopic Instrument DESI, measures BAO very precisely. And what it has found is that our understanding of dark energy is not correct. So we parameterize dark energy as lambda, which is this center of this dotted line, of this dashed line here, 0 and -1. But what DESI finds is that our universe should have a different model for dark energy. And hence it has found some evidence of dynamical dark energy at a 4 sigma certainty. So now we see those two results were published in this year. Two different experiments. One is a CMB experiment, one is a galaxy survey. One suggests here ACT, that Atacama Cosmology suggests the CDM is correct. But DESI suggests there is some problem and lambda CDM is not correct. So we are at kind of like a fork road where different experiments are still giving different results, and our understanding of the universe seems to be rather incomplete. Now, this is to some extent where I come in. What I basically do is I combine different data sets in a statistical sense and try to understand something more about our universe based on cross correlations. So cross correlation is basically a tool in which you can combine different data sets to understand the fundamental nature of the universe. So, for example, the two surveys can be galaxy surveys like DESI or LSST, which is upcoming, and CMB measurements. We can combine these two and understand about the underlying physics. But there are a lot of things that we have to worry about. There are a lot of systematics, and there are a lot of caveats that one has to be very careful about. So I will just share one of the important results that we published rather last year. So you can do this cross correlation by dividing the galaxies into very narrow bins, into redshift slices. And this method is called tomography. And this tomography is a rather more powerful tool because you can use this tomography to understand how parameters, cosmological parameters like the strength of strength of clustering, or the rate of expansion, the Hubble parameter or the S8 parameter, evolves with time. What was its value before? What is its value now? So you can learn all of this if you do this tomography. So in a recent study, we found that if you have a galaxy survey, which which a photometric galaxy survey, then the redshifts that you measure will have some errors, and they are called photometric redshift errors. And due to these errors, when you divide galaxies into redshift bins, there will be some leakage. So, for example, if your true redshifts are like this orange dashed line, your photometric redshifts will be like this blue curve. And you see, instead of all being between zero point 0.4 and zero point 0.6, there is some galaxies leaking into outside this range. And this can change our understanding of cosmological parameters. And indeed, we have shown that if you do not properly account for this leakage, you will measure a wrong value of S8. So the true value of S8 was 0.832, but what you will measure is 0.792. And if you remember, this is exactly the 2 or 3 sigma tension where S8 is. So what we did was we proposed a method to correct, to account for this leakage, which we call the scattering matrix. So basically this method tries to compute the fraction of galaxies that has moved from one redshift bin to the other and tries to correct for this effect. And once you correct, you are back to where the true value is. So if you see that without scattering matrix, you measure a biased value of S8, and then you will infer, oh, that there is a tension in the S8 parameter. But with the if you apply the scattering matrix approach, you recover back your true value of S8. So, and it's not just the S8 parameter will be biased. In a recent paper this year, we showed that if you try to understand the dynamics of inflation, the very early period of the universe, and based on this distribution of galaxies, and if you do not use the scattering matrix approach, you will measure wrong values of you will have wrong inferences about this inflation. And only after you use the scattering matrix approach is that you can predict correctly what the dynamics of inflation are. Okay, so this brings me to the last part of the talk today. So we have seen uh, what recent results from surveys like DESI and ACT are telling us about our universe. We see that we have learned that they are not consistent with each other, and there is still something missing in our understanding. So what hopes can we have from the future? So very recently, very soon, we will have the Vera C. Rubin LSST survey, which is a ground-based photometric survey in Chile. It has a 8.5 meter primary mirror and a 9.6 square degree field of view. It will observe southern sky, the southern hemisphere, 20,000 square degrees in 6 photometric filters, U, G, R, I, Z, and Y. It will operate for 10 years, and the 23rd of this month, we will have the first image from LSST. It will map the distribution of dark matter. It will help us understand how the structure, how the matter is distributed in the universe, how galaxies are distributed, and it also helps us understand dark energy. Other than this, it will also be useful for supernova cosmology and also time domain astronomy. We already had Euclid. Euclid is up in space. It's a European Space Agency mission. It's an ongoing space-based survey, a spectroscopic and photometric survey. It will cover 15,000 square degrees of the sky. It will run for 6 years, and it will observe roughly 1 billion galaxies, which will be used for understanding this lensing that we were discussing when we discussed dark matter. And recently, some data from Euclid was released to public. So if you're interested, you can look at this data. For example, here in the right is the images from Euclid. So we see this Horsehead Nebula. You can see how precise and how clear the images from Euclid are. So we will be able to understand our universe with a much higher precision than before. Also, we have SKA, which is Square Kilometer Array. It is the world's largest radio telescope. I'm sure you all know about it because the SKA Mid telescope is hosted in South Africa, and Australia hosts the SKA Low, the dipolar antennas that you can see here on the top. So what SKA will do, it will measure the distribution of hydrogen in the universe. It will also measure baryton acoustic oscillations, and it will help us test the general relativity, the theory of general relativity. And in addition, this will be the first time that we will be able to measure, to probe and understand dark ages. We till now have no survey that goes as behind in time as to measure as to understand dark ages. So SK will be first of them. And it will also be the largest radio continuum survey in the world. And Africa in general plays a very big role in SKA because it hosts the entire SKA mid array. So these were all the galaxy surveys that are that will become that are either ongoing or on in our line, or it will be in the future that will help us understand our universe. In terms of CMB experiments, we have the Simons Observatory. It is very close to the Atacama Cosmology Telescope, the ACT results that we saw. It's also in Chile. And what it will detect is gravitational waves. So it's generally assumed that due to the Big Bang and period of inflation, there is a gravitational wave that propagated from that event, and it will try to detect that primordial gravitational wave. So we will be able to probe the very, very early universe when it was just beginning. Other than that, we will also learn something about neutrinos, that what are its masses, what are the types, and most importantly, we will learn about dark energy and how the structure grows in the universe. In addition, there is also a Japanese space mission called Lightbird. It will be launched in 2030s, and it will also try to measure CMB polarization and try to detect the primordial gravitational waves and try to study how our very early universe was. And it will directly help us to constrain models of inflation so that we know better about the inflationary period where which we do not have a good idea about right now. Now, this is a mandatory slide about how Africa plays a part in the cosmology, in the global cosmology. So first of all, Africa hosts some of the major radio surveys in the world. For example, Meerkat, SKA will be in Australia, ASCAP is in Australia, HIRAX is in Africa. Uh, so all of these combined is basically putting Africa into the point where they can lead radio analysis and radio cosmology in the world. Africa is also part of the Vera-C-Rubin LSST survey, the in different astronomy related fields. Other than that, due to these different SKA telescopes and the Meerkat and the ASCAP surveys, which are hosted in Africa, I believe Africa community can lead areas like radio cosmology and intensity mapping. And with continued international collaboration and research exchange, I think we can all do a much better cosmology in general. So probably this is the best time that we focus on training the new generation of scientists as well as engineers, because engineers are very important in our understanding of cosmology. They are the ones who make it possible that we understand our universe. And public outreach, seminars like this, which we are attending right now, is also very ingredient to promote open science. So To conclude all our discussion today, is that lambda CDM still is remains as our best understanding of the universe, as the best framework in which we can model our universe. But there are some key tensions which remain. And now there are a variety of observations like CMB, acoustic oscillations, supernova, weak lensing, that helps us understand our universe. Recent results from DESI and ACT are testing the lambda CDM model to the very extreme and are trying to show that there is some problem with our understanding. There is some missing information, missing ingredient in our understanding of the universe. And with future missions like LSST, Euclid, SK, and others, they promise, they hold the key to do some transformative cosmology and to make some revolutionary discoveries in the future. And together we should look onto some of the really big questions that are there in the universe. For example, why do why do we still have like H naught and S8 tensions? Is it some hint of new physics, or is there something that we have not accounted for and some unsolved systematics? What is dark matter made of? Is it new particle, or is our understanding of gravity incomplete, or is it something completely different which we know nothing about? Similarly, what is the nature of dark energy? Is it really a cosmological constant? Is it really lambda? Is it some new kind of force field or something else? Another important question which people are now asking is, can we really measure, just like we have the cosmic microwave background, can we also measure a background of neutrinos? If we do, we will be able to study the universe even earlier, even before the time when universe was 380,000 years old. Again, if and another important question is, did inflation really happen? It is our model. We have not seen inflation happening. It is our model, it is our assumption that inflation happened. So, can we detect those very early, very primordial, very nascent gravitational waves and test inflation? And finally, the most philosophical and fundamental question of all, how and why did it all begin with the Big Bang? And who knows, some of these questions may be answered by one of by a group of African cosmologists, and will be very happy to learn something new by the continued collaboration and effort. So with this, I thank you all for listening, and if you now have any questions, I'll be happy to answer them.
Um, Thank you very much, Dr. Chandra, for the very nice talk. Now, Teddy is raising his hand. You can go on, Teddy, with your question.
My question is on the dark matter and the dark energy. Uh, in the beginning, when I started to get the understanding of it, I was thinking that it's something that is undetectable. We can't know anything about it. Then later on, I looked at the dark energy. Now, in getting the dark energy, for us to have the energy, it's possible that it's coming from collision of objects, mergers of galaxies, supernova, and the other things. Also, if there are collisions, we expect to have photons, we expect to have electrons that can further give us the understanding of dark matter. Now, from the studies so far, it's clear that we don't really understand what dark matter is. So my question is it we know already in a wrong way or in another way that is making it difficult for us to understand it? Because if there is energy coming, possibly maybe from radiation or from collision, merger of galaxies, merger of stars and other objects. So is it not that we are dealing with what we know? Possibly, if those things can be looked at, and in a different way that is making it difficult for us to understand what dark matter is.
Sorry, but can you please
Uh,
repeat the question at the end? I think you broke up and we couldn't
yeah,
hear.
I thought so
Okay.
too. Just the question and be concise.
Okay, the last question was the question was is that since this dark matter is able to produce energy, so looking at it, there is a possibility that maybe it might be emitting some kind of radiation, or maybe collision. In the collisions, we have electrons and protons that are emitted. Then also other parameters that can help us understand that we are dealing with what we know in a different way. That is making it difficult for us to understand that much.
So, if I understood correctly, your question is, can the collision between the fundamental particles like electron and proton can be used to explain something like dark matter? Did I get it right?
Okay, my question is after the collision, there we know we can get electrons, photons, and other things that we observe.
When you say other
Also,
things, uh,
I was at the energy itself. Energy can be from radiation, emission of radiation, meaning dark matter is emitting radiation. Or
okay,
collision of different objects which are dark matter as well. Then possibly from collisions we may have it may emit electrons and photons, maybe
no, so
other things like neutrinos or what. Now,
no,
if
yeah,
if that be the case, because we are able to get with what we know in a different way, that is making it difficult to understand it.
okay. So I think I more or less understood what you're trying to ask. Is that given that these different kind of interactions, are we basically not able to understand the same interactions in a different way? uh, I would say that the answer is no. So because, okay, the all the kind of interactions, for example, when you're talking about collisions, and then due to collisions you have electrons, protons, and all type of, for example, neutrinos, and then there is some energy that goes into it. We can detect all of it, right? It's not that we don't have the means to detect those collisions. That's exactly what, for example, the Large Hadron Collider at CERN is doing. So let's assume for a moment that these collisions are happening in galaxies, and these will generate some particles. It will generate some electromagnetic signatures, electromagnetic waves. Now, we have all the means to detect those electromagnetic waves. And as I mentioned, that dark matter is necessary because we already have means to measure, to see all the radiation and all the light that is coming from the object. But still, the effective mass of the system is larger than what we basically measure compared to these observations, these electromagnetic observations. So if you're thinking in terms that we have collisions, we have electrons, protons coming out, we have some energy, and basically we are not able to understand this kind of system, it seems highly unlikely. uh, I believe our understanding of the standard model of particle physics is very sound, and we basically can predict as well what kinds of interactions will lead us to what kind of particles. And based on that, I would say it is unlikely that it is something that we already know. Uh, there are more chances of this being something unknown, or in terms of uh, some fundamental assumption of our cosmology needs to be violated in some sense. Purely in terms of known physics, I believe dark matter is not being able to explain yet. I mean, I hope I
o-
answered what you asked.
okay, thank you. We'll be able to take one more question before we round off. Do we have any other question? Okay, then maybe I will ask one.
Sure.
You talked about flatness of the universe, and that reminded me of the Middle Ages when there were debates about curvature of the earth or flatness of the earth and all that. And then in that case, if you assume that the universe is flat, are you implying that they have finite edges? Literally, if we should talk about it literally in that sense, because a flat surface should have a finite edge where you might get to that place and eventually you slide into an unknown place or another whatever that you may tell us if such thing exists, or such flatness of the universe is defined in terms of another concept. Would you clarify more on
Sure.
what you talked about regarding the flatness of the universe?
So first thing, mathematically speaking, flat spaces doesn't have to be finite, right? You can think about a piece of paper that's infinitely large. It will still remain flat, right? And that's purely mathematically speaking, right? So it's not necessary that, that given a flat geometry, you will reach an end and then you will slide off, right? Also, when we talk about uh, flatness, it's basically the geometric property of the universe, right? And this flatness has more to do with mm, how you measure distances, how you measure angles on the sky, right? For example, we know that if we have a ball, the sum of the angles of a triangle will not be 180 degrees. It will be higher than 180 degrees. So the sum of 180 degrees only happen in flat surfaces. Our Earth is a not is not does not have a flat geometry. It has a curved geometry. It is a positively curved geometry. So if you make a sphere on the or if you make a triangle on the Earth and you try to measure all the angles, it will be more than 180 degrees. Similarly, this is the type of flatness that we are talking about. So what changes is the way you measure distances, the way you measure angles changes if your universe has a different geometry, that it is flat, whether it is positively curved, whether it is negatively curved. And we can use measurements like CMB, measurements like galaxies, BAO, to basically constrain what should be the curvature, what should be the flatness, how flat our universe should be. Should it be exactly flat or slightly positive, slightly negative? We can constrain it very precisely.
Okay, thank you. We're rounding off, and in our midst, we have Professor Fulvio Franchi, uh, who incidentally is the PI of this project, the PI of FAST4Future. I wanted to tell him to.
Okay, I'm here.
Oh, okay, yeah.
I was about to leave.
Okay, that's good. So maybe you can round off the program, and
Yes, thank you
then
very much, as usual, for the organization, to the colleagues at University of Nigeria, and thank you to Dr. Saraf for participating in this project. It's always nice to see these cutting edge research topics, which I'm a geologist, so I don't really grasp the topic, but I'm happy to see this type of research. I hope you will agree in uploading some material on our virtual center of excellence, so that all the African students that are following us and were not able to join today will benefit from your science. It's difficult to get people to seminar these days because there is literally one seminar a day. So students are spread very thin, but we do our best to disseminate. And thank you very much, Dr. Chandra Saraf, for sharing with us. And thank you to Christian and Professor Odu for the organization.
Thank you. Thank you for
thank
inviting
you.
me.
Okay. So this marks the end of our program today. Thank you, Chandra, for coming. And thank
Thank
you, Prof. Fuvia, for your closing remarks. So see you in July during the July seminar. Thank you.
you. Bye bye.
Bye.